Okay, and I'm going to share. All right, I don't want that actually. My mistake. Let's see, I wanted to go. All right, this is where I wanted to be. Sorry about the confusion. Okay, so this is section 2.3. And this is starting out with prime numbers. And sometimes prime numbers were taught in school and sometimes they weren't. Sometimes they thought, oh, this is so hard, students shouldn't learn it. And the truth of the matter is they should have, because it was the breakthrough of why everybody has trouble with fractions. Now, prime numbers, just as a review, are numbers that you can only multiply them one way. So a perfect example of a prime number is 13. The only way to multiply 13 is 13 times 1. There's no other way to do it. 13 times 1, that's it. And so there are a whole bunch of numbers that are considered prime, and they're important because they're the building blocks of everything else. So the lowest prime is 2. And 2 qualifies for this definition because the only way to get it through multiplication is to multiply by 1. The next one is 3. The only way to get it through multiplication is 3 times 1. Okay. The next number you'd think is 4, but 4 is no good because everything multiplies by 1. That's no big deal. But 4 also has these 2 factors. And so when there are other factors besides the 4 times 1, it's not prime. It's called composite. It's composed of other factors. And so we can't call it prime. And so the next prime number is 5. So 5 times 1, if you think about it, that's the only way to get 5 in multiplication with whole numbers. And so 5 is prime. And then you think about 6. 6 times 1 is perfectly good, but then you have 2 times 3. And what you're probably beginning to see is that we don't, from here on out, we'll have no more even numbers because every even number will have a factor of 2. So in order to get us a decent list of prime numbers, we have to just look at the odds. So I'm going to look at 7. 7 times 1. If you can't think of anything else, it's prime, right? How about 9? 9 times 1, of course, but then you've got 3 times 3. That makes it composite and it's not prime. So what I'm going to do next is after 9, I'm going to 11. 11 times 1 is 11. That's the only way to do it. 11 is prime. I'm going to make us a beautiful list in a minute. 13. 13 times 1. There's no other way. 15 is not good because of 3 times 5. And so it's automatically eliminated. But 17 is prime. Okay, so prime numbers are mostly odd numbers, but not all of them. The only even prime number is the very first one, and everything after that, the even numbers are no good. I'm going to do 19. 19 times 1 is also prime. So what I want to do is make us a list of what we have so far. So prime numbers, and this is something that you should be able to rattle off at least up to this number we just did. The 2 was good, the 3, the 5, 7, 9 was no good, 11, 13, skip 15, 17, and 19. They continue, they keep going. This notation is a way of saying this is a group of numbers, and these are the prime numbers. The lowest is 2, and it does keep on going. 21 is no good, but 23 is prime. 25 is not because of 5 by 5. 27 is not, but 29 would be prime. And they go on into huge, huge numbers. You know, 10 or digits across, there's a prime number. And prime numbers are used in technology to help encrypt data. You know, when you have your credit card and they say it's encrypted, they're using some little thing with a crazy old prime number that's way out there. So these are useful in that way, but these are prime numbers. So here's the statement. Any whole number is prime or a multiple of primes. So for instance, if you take the number 10, it is not prime, but here's what it's made up of. 2 prime numbers. And so if it isn't prime, it's composed of prime numbers that are multiplied together. Now, it's not just 2 of them. It could be 3 or 4 or 5 of them. But these are the building blocks of 10. This is telling me that there's a factor of 2 because it's even. There's a factor of 5 because 5 goes into it nicely. And so it's going to help us with fractions. So what they try to do is the number 12, for instance, and I'm going to show you how to break this down into prime factors. The number 12 is not prime. Obviously, it's even. That kills it right off the bat. And so there's 2 ways to find out the exact prime factors. There's 3 of them. One way is called a factor tree. You think of any 2 numbers that multiply to get 12. And I'm just going to start with 2 times 6. Okay. Now 2 is prime, so there's no point in trying to break that down any further. It doesn't. But 6 does break down further. So 6 is not prime, but it could be broken down into 2 times 3. So what I ended up with, I'm copying that first 2. These are the prime factors of 12. So it's a pair of 2's, 2 times 2 times 3. And if you ever need to know if you've done this correctly, just multiply it out and see what you have. 2 times 2 is 4, times 3 is 12. This is correct. These are the prime factors of 12. And I'll show you in the next lesson or 2 why this is going to help us. It's going to help us here, but it's also going to help us in other situations. Prime numbers are important. And so if they taught it to you, good. If they didn't, here we're going to do it. So the second way to find prime factors, and in some ways I kind of like it a little bit better, is the following. It's called division, and it's actually short division, and we're kind of going downward. I look at this number 12 and I say the first number that I can think of that's prime that goes into it is a 2. So I might as well use 2. There's no point in going for higher. So 2 goes into 12 6 times. Now, if this was prime, we were done, but it's not. And I noticed I could go 2 again, so I might as well. So 2 goes into 6 3 times. So my answer actually is right here. So I would say it's 2 times 2 times 3. Okay? I kind of like this method a little bit better, although both methods work perfectly fine. Because what I'm doing is I'm starting with 2. Is this number even? If it is, let's divide it out by 2, making it a smaller number. As you go further down, it gets easier and easier because you're working with numbers you're more familiar with. But either way, both of these methods work. Sometimes, because it's 2 times 2, they'll write it as 2 to the second power multiplied by 3. So both of these are correct answers. And when they ask you which way, for me, either way is good. But if they want it like this, then you give it to them like that, 2 to the second power. Now, sometimes the number is larger, and I'm kind of looking at the textbook, but only as a reminder of what we're doing. If you had to break this down into prime factors, obviously this is a number, it's not like 15, you could say 3 times 5 and be done with it. You're going to have to do a little work. I want to again show you this method. Because it's even, it ends in an 8. I'm going to divide by 2 and cut this down a bit. So 2 goes into 10 5 times, nothing left over, right? And 2 goes into 8 4 times. Well, it's a smaller number. That's good, but we're not done. So I'm going to use 2 again because why not? It's even, and that's easy. So 2 goes into 5 twice. Now, with a 5, there's 1 left over, and I'm going to put the 1 left over here. And I'm going to read this as 14. So this is short division. And if this doesn't appeal to you, if it seems too much, you might do it another way. But I'm going to show it this way. It's not too bad. 2 into 14 then is 7. I cannot use 2 again because this number is odd. And so 2 will not divide it. But I'm hoping you remember from last class what I said about numbers like 27. This shortcut for 27 is valuable to you because 2 and 7 is 9, which means that's a multiple of 3, which means 3 divides it evenly, no remainder. And that's what we're looking for. 3 into 27 is 9. Well, this problem has one more step because 9 is not prime. You remember your list, 9 is not on it. But now you know the result. 3 into 9 is 3. So your answer is here. So it's 2 times 2, and then 3 3s. And the alternate way to write it would be 2 to the second power multiplied by 3 to the third power. Is that okay? So that one was more trouble, but what I did is I started easy. I started with the bottom, the lowest prime. Because it was even, I used 2 until I couldn't do it anymore. The next important one is 3s. Try 3s, and I can easily see 27 divides by 3 multiple ways. This is one of my favorite problems. Don't ask me why. I'm saying, what are the prime factors of 51? This is nothing on your multiplication facts that you memorized. 51, looking at this just carefully, not too carefully, it looks like it's prime. Nothing does 51, right? Wrong. Nothing divides 51. Why? 5 plus 1, 6. This is where that rule of 3s, multiples of 3s, help you out. This number divides by 3. And it's not obvious. And this is where, they used to just give you problems where it was so obvious. This is not obvious to me, but 3 clearly divides this, and we're going to do it. 3 into 5 is 1. How many left over? Well, 5 minus 3 is 2. I read this as 21. 3 into 21 is 7. The prime factors of 51 are these. And this is not the kind of thing that anybody would get, but because of this rule, this allowed us to beat this problem and figure it out. And so as the numbers get higher and you're not familiar, you never saw that one before, this is where I think the rule of 2 for evens and the rule of 3 and the rule of 5 will get you almost completely through most of your problems. So I just wanted you to see about that. And so let's see how this might be used. Sometimes people, one of the first things we do with fractions is reduce them. And that means we want it into lowest terms. And so we want the equivalent fraction, but in lower terms. Now, some people have learned, well, okay, I got this. They both have factors of 3. And remember, 15 is 3 by 5, and 12 we did earlier was 2 times 2 times 3. They both have a factor of 3. So if I decide to divide everything by 3, this is one approach. And so in your head, you probably don't write this, but you're saying to yourself, I'm going to divide both of them by 3. Okay? I'm not saying you have to write this, but this is what you're thinking. 12 divided by 3 is 4. 15 divided by 3 is 5. So when they say reduce it, you're going for an equivalent fraction that's exactly the same. 4 over 5 or 4/5 is the same as 12 over 15. And so that's what we're trying to do. Now, occasionally you get a problem where you start the numbers are too high and you're starting to make mistakes when you try to reduce them. This is the case for prime numbers. Now, this might not be hard enough to need it. Clearly 15 was 3 by 5. And I'm hoping you remember from before when we did 12, the answer was this. If I didn't know it, I could do it real quickly. 12 is 2 times 2 times 3. But this is why this canceling or dividing by the same number worked, because we have a 3 in the numerator and a 3 in the denominator. And 3 over 3 is just equal to 1. It doesn't change the answer, the result of this. And so this is why I can actually do that canceling. And there's nothing else to cancel. I can't cancel a 2 with a 5. And so I have no choice on this except to multiply across. 2 times 2 is 4. 1 times 5 is 5. And there's the answer. Now, I know I've made a big fuss about doing this, but sooner or later, we're going to be happy about this when we get in trouble and we cannot figure out what needs to be done. So let me see if I can find, has anybody tried any of these? As the numbers get larger, the problems occur about reducing. And so what I'm saying to you is if you can successfully reduce this, the old cancel way, do it. I have no problem with doing things correctly. If you find that you're starting to make mistakes as the numbers get larger, you might consider prime numbers as one way to beat it. And so we never forget that prime numbers are out there to help us if need be. So if I try to reduce this by canceling, one thing I might notice, and this might take me several steps, but I'm going to show it to you a couple of ways. Since they both are even, they would both divide by 2. So I'm going to take 66 and divide it by 2, and I'm going to get 33. And I'm going to take 84 and divide it by 2, and I get 42. Now, that looks considerably better. It's smaller, lower terms. The question is, are we done? Now, they're not both even anymore, but I'm going to keep at this little trick. 4 plus 2 is 6. That divides by 3. And so 33 is really just 3 by 11, isn't it? And so there's no 11s here, but I'm going to divide both of them by 3. And I'm writing this up here. You don't have to write it. But 33 divided by 3 is 11. And 3 into 42, if you can't do it in your head, do it on the side somewhere, and don't, do it away from the problem so that this doesn't get out of control. 3 into 42 ends up being 14. The question is this totally reduced? And the prime numbers will help you see that it is done. And sometimes people get to the correct answer and then they keep going. I don't know, they just can't stop themselves. But 11 is prime. So the only way to get it is times 1. 14 is not prime, but it's small enough that you should know it's 2 by 7. Even if you don't write this, this is what's going on. There is no common factor from the top to the bottom, the numerator to the denominator. There's nothing to cancel. Therefore, this was the finished answer. Okay? So the fact that this was prime doesn't cinch it. But when we look at the factors of 14, there's nothing there. There's nothing common. Now, the same problem with prime numbers. And I want you to occasionally try this, even though so that you can do it successfully when you need it. 2 into 66 is 33. 2 does not go anymore, but 3 clearly does. And 3 into this is 11. So those are the prime factors of 66. I'm going to now do 84. I'm going to use 2 again because it's even. 2 into this is 42. I go 2 again. This is 21. You probably realize this is odd, so I'm going to use 3 and 7. This is done. So here are my prime factors, and I'm going to write them in the fraction. 2 times 3 times 11 for that top number. 2 times 2 times 3 times 7. So all I did was copy the answers I got from doing the prime factors. This I call the skeleton view of the problem. Nothing is hiding. There is no way you're going to make a mistake because you can see every little bit of this problem. And so what you can see is there's a pair of 2s, top and bottom, that can reduce, and you would replace it with a 1. There's a pair of 3s, which you could also reduce. And now all you've got, forget the 1s, you've got 11, and you've got a 2 and a 7. There's nothing to do for that. That one is complete. So this is 1 times 11, 11. The 1's not going to change anything. 2 times 7 is 14. And when you see it in this form, you know there's no way this is going anywhere. Because you can see there's nothing left to cancel. And so I'm not saying, you know, for a simple little problem like 6/10, you don't need to make a fuss. But as the problems get harder, sooner or later, you're going to say, oh, I could really see the answer to this if I had prime numbers. And I'm going to go back to a version of my, remember 51? Both of these divide by 3. 5 and 1 is 6, that divides. We did this earlier. 5 and 7 is 12, that's a multiple of 3. They both divide by 3. And so I don't know if you remember, but 51 was 3 by 17. I'm sorry, I'm thinking ahead. This is 3 by 17. 57, on the other hand, 3 into 5 is 1. There's 2 left over. I'm going to put the 2 here and read it as 27. 3 into 27 is 9. This is where the 19 belonged. So this is 17. This is 19. I can tell. There's no way to make a mistake at this point because everything is out in the open. There's nothing hiding in that 51. This is 17 over 19. I think this is just a demonstration problem about where the prime would start to kick in and be useful to you. Whereas before they would just give you problems, well, everything turned out just fine, and they never would give you a hard problem. Well, sooner or later, they're going to say, oh, wait, here's a harder one. And you want to be able to deal with it. And so that's when we go after primes. Can anybody think of a question? So most of this is reducing. I don't know if anybody's, sometimes people go ahead because there's no way to stop. But if not, well, I'm going to go on and see what's in 2.4. So this is multiplication, and in a sense, we've already been doing it. So this is 2.4. And I'm going to show the various kinds of multiplication of fractions. And so the 3 and the 2 are both in the numerator, and the 5 and the 7 are both in the denominator. And what we want to do is see if we can't cancel. Now, if the 3 could cancel with the 5, or the 3 could cancel with the 7, but unfortunately the numbers aren't right. So when you find there's absolutely no way, and you can actually see this problem like this, although you don't really have to write it like that. But the 3 and the 2 belong on top, the 5 and the 7 belong on bottom. Does anything cancel? No, you don't have any pairs. So in this particular case, there's nothing to do but multiply across. So 3 times 2 is 6. 5 times 7 is 35. And then I asked you the following question. Could this be reduced? And you're thinking, well, maybe, I don't know. Well, here's what I want you to say. If it can't be reduced here, it's impossible that it can be reduced here. So you don't have to fuss with this anymore. If you looked at this carefully and saw nothing, this can't be reduced. It is done. So let me try another version. 3/5 times 8. Now, the thing about multiplying fractions is what you need is nice simple common fractions for both numbers. And so 8 should be written as 8 over 1. Then you can clearly see what is the numerator, what is the denominator. And so this particular problem, I don't see anything numerator, top and bottom that cancel. So again, I'm into this. 3 times 8 is 24. 5 times 1 is 5. And if they expect you to write it as a mixed number, then you do it. Otherwise, 24 over 5, in my opinion, is a perfectly good answer. It is reduced, which means there's no common factors left. And I did notice in one of these examples, they left it. So look at the instructions and see what they're actually asking for. And I'm gonna copy this one. Okay, this was, one of the examples they showed. The truth is, this is straight, everything is multiplied. The fraction, everything is multiplied. If you wanted to follow it by order of operation, we would do what's inside the parentheses first. And so I'm going to try to ignore the 1/2. Does anything cancel anywhere? There's any common factors? I don't see anything, do you? So 3 times 1, I'm going to write it as 3. 4 times 5 is 20. That's that. And then there's the 1/2. And because there's nothing here and because there's parentheses, this means multiply. If you want to put a dot in there, go right ahead. The 2 and the 3 do not have a common factor. The fact that these are both in the denominator, you can't cancel them. You've got to cancel numerator and denominator, and these are both denominator. I've no choice but to proceed. 1 times 3 is 3. 2 times 20 is 40. That's all I can do. That's the end of that, okay? Now, running out of paper, I'm gonna go get some more. Now, I want to talk about one word. If I said 1/2 of 50, there's a number here, there's a number here, and this is the word of. When the word of sits between two numbers, it means multiply. And so this is, so when you can say, you want a 1/2 of something, it's multiply. So this problem becomes 1/2 times 50. Now 50 needs to be a fraction. And so what I can do with 50 is write it as 50 over 1. Okay, so this had that one word in it. I turned it into what the correct multiplication. And now I'm going to do this problem. Some people say, okay, well, what I'm going to do is multiply 1 times 50 and 2 times 1 and then deal with it from there. In general, the best approach is to cancel the problem now before you get to the final answer. Because if you get your answer too big, it makes it a lot harder to deal with. It's easier to see what needs to happen at this stage. And so I'm going to encourage you to cancel it or do something with it now. I think 2 and 50 is fairly easy to see. They both divide by 2. I'm going to show the cancel method. 2 goes into 2 once. 2 goes into 50 25 times. So now I say, well, 1 times 25 is 25. And 1 times 1 is 1. And although that's 25 over 1 is correct, in mathematics in general, what people want is the simplest answer you can provide them. Almost always. In other words, you don't want 100 over 4 or, 50 over 2 or 25 over 1. You want the simplest way to say it. And that would be just straight 25. And so this is clearly preferred. Okay, this is not wrong. This is preferred. And so that's what I want you to do. The other thing I wanted to do next is, what do you do when you're asked to multiply a mixed number and a whole number, or even two mixed numbers? And so remember the skill we learned about turning this into an improper fraction? We're going to use it here. 2 times 1 is 2, plus 1 is 3, and this is over 2. Remember that? And I'll continue to do a few more. The 5 needs to be a fraction. So here's the deal. Mixed numbers become simple fractions, and I'm going to call this a simple fraction because there's nothing wrong with it. The book calls it improper, but this is easier. This is the better way to do the problem. So this is preferred. 5 becomes 5 over 1. And so what we're looking for in each multiplication is simple fraction times simple fraction. And you fix it until it's there. Then you look to see if there's any common factors anywhere. I don't see any. So at that point, you multiply across. 3 times 5 is 15. 2 times 1 is 2. That is a reduced fraction. It's a perfectly good fraction. If they say, well, write your answer as a mixed number, you could. This is a good answer. And so you just follow the instructions. So let's say they said mixed number. I don't care. But let's say they did. You would divide 2 into 15. That would be 7. That's 14. There's 1 left over, 1 over the 2. So both of those were good answers. And so we're just going to follow those instructions. But let me find ourselves another one. Doing this in this form would be awful. I'll tell you that right now. So what we're going to do is turn them both into simple fractions, improper. See, I hate that word because it sounds like they're not right, but they're perfect. So here's how we do it. It's 4 times 2 is 8, plus 3. 8 plus 3 is 11 over the number 4. This one needs to be turned into a simple fraction as well. 5 times 3 is 15, plus 1 is 16 over 5. Okay, I've now got it in good form. I'm looking at the problem now. The 11 and the 5, there's no hope for that. But the 4 and the 16, I could reduce it now. And if you want to, I could divide both of these by 4. 4 goes into 4 once. 4 goes into 16 4 times. At this point, I've got nothing that looks like it's going to be common. And so I'm going to just multiply across. 11 times 4, 44. 1 times 5 is 5. This is reduced because in this part of the problem, everything is reduced. So people confuse reduced with make it a mixed number. This is reduced. There's no common factors left. And so this is an acceptable answer, or the mixed number version of it is an acceptable answer. I'm going to leave that one there because I like it. This particular section has one geometry formula. I didn't draw it so perfect, but there it is. I'm going to start with this triangle. And what I want you to do is remember the formula for the rectangle. And so this would be the length, and this would be the width. And when you had to find that, the area was the length times the width. Is that right? So in a rectangle, if this was 3 feet and this was 5 feet, the area would be 3 feet times 5 feet, which is 15 square feet. Now what I want you to do is look at the triangle, and I could have drawn it better, so I'm gonna try again. Okay, there's my triangle. I'm putting little dotted lines to help you. How does this triangle compare to the rectangle? Can anybody say?
It's half.
It's half. Well, if you can see that visually, you've got the formula. Because if this was 3, and this was 6, let's see. Let's have this be 3 feet. Remember, this little mark was for feet, and let's let this be 6 feet.
Professor, can we go if we need to? Because
Oh, certainly. Yeah.
okay, thank you. I'm
Oh, I'm
trying.
sorry. I didn't realize how late it was. Okay.
Okay,
So
thank you.
yeah, let me just finish this. And if you have to go, that's fine. And then I'll stop the recording. So 3 times 6 would have been 18 if it was a rectangle. But what is it going to be when it's a triangle? Half. Okay. So the formula goes like this. Instead of length and width, they call this the base and they call this the height. So the formula goes area equals 1/2 multiplied by the base multiplied by the height. But really the base in this case was the length, the height was there. And so this becomes the formula for the thing. And I see it's quite late, so I think I will stop. So I'm going to stop. I'm going to stop recording for starters.